everyone and welcome. My name is Christina Petschnigg and I want to thank you for taking your time to watch my presentation on our paper, A Heuristic Search Algorithm for the Collaborative Freighter Delivery Problem. Let's start by looking at the current state of the logistics sector. In 2018, the transport sector accounted for about 21% of global CO2 emissions, with road-bound freight traffic being responsible for nearly 30% of this total. Freight traffic demand is projected to triple between 2015 and 2050, and even with the current mitigation policies, transport-related CO2 emissions could rise by 60% by 2050, driven largely by freight traffic. Addressing this requires innovative solutions, including reducing empty truck journeys, which increased in Austria from 31 to 45% between 2010 and 2019, suggesting significant optimization potential. While individual companies are effective at optimizing their operations, the real challenge lies in cross-company collaboration. A sharing economy in logistics could help address the aforementioned challenges by improving resource utilization, reducing empty truck drives, traffic, and cost through increased load factors. However, realizing such a sharing economy requires overcoming two key challenges. The first one is related to privacy. Companies need a trusted environment that ensures their data remains secure, and the second challenge is related to optimization complexity, as collaborative logistics increases the scale and complexity of already difficult optimization problems. Our paper now focuses on the second challenge, presenting a heuristic approach to solve an NP-hard optimization problem in collaborative freight logistics. The major contributions of our paper are the following. We formally introduce the collaborative freighter delivery problem, and we demonstrate that the problem is NP-hard. Further, we propose a resource-saving anytime heuristic designed to minimize empty truck drives, which has the potential to significantly enhance operational efficiency. Lastly, we present the results of an experimental evaluation of our heuristic using a publicly available benchmark dataset. Our findings highlight the effectiveness of our heuristic and the comparative benefits of operating in a collaborative versus a concurrent freighter setting. Let us now look into the definition of the collaborative freighter delivery problem. Given is a map listing positions and distances, where positions correspond to, for example, warehouses and production sites, and distances correspond to road-based distances between these positions. The area defined by this map is operated by a set of collaborating freighters, each of which possesses a fleet of trucks and a set of customer orders. Every truck is associated with an initial position and has a maximum loading capacity measured by the number of standard Euro pallets it can carry. In addition to trucks, each freighter manages a series of customer orders, which are defined by a specific volume and designated pickup and delivery locations. A solution for an instance of the collaborative freighter delivery problem corresponds to a set of truck drives such that all orders are completed, transporting items from their pickup points to their delivery locations. Each truck drive is executed by a single truck starting from its current location, which must match the drive's start point. As each truck drive only has a single start and goal, a truck drive only transports orders with the same start and goal positions. Further, truck drives for the same truck cannot overlap and must begin from the goal position of the previous drive or its initial location. The nature of these constraints occasionally renders empty truck drives inevitable. Each solution has an objective value based on a specific optimization criterion. In this case, our optimization criterion corresponds to the normalized average empty space per kilometer traveled across all truck drives. Let us now examine the formal definition of the inputs to the collaborative freighter delivery problem. We start off by defining the environment, which consists of a map denoted as M and which corresponds to a directed graph. This graph comprises a set of positions P and road connections R, along with a distance function D, which quantifies the road-based distances between these positions. As mentioned before, in our framework we have a set of freighters denoted by F, and all of these freighters possess a fleet of trucks, which is denoted by T, and a set of orders to be delivered to customers, which is defined by O. Let us now look further into the trucks over here. So each truck has a capacity C and an initial position I. And looking into the orders, an order is defined by its volume V, and it also has a start and a goal position S and G. To provide a concise understanding of the optimization problem, let me now outline the key aspects of the solution and respective constraints. A solution corresponds to a sequence of truck drives, which we can see here, and each truck drive must be associated to one truck out of the fleet of trucks, which we can see over here. And also each truck drive must have a specific start and goal position out of the set of positions. Further, we must ensure that each truck drive is linked with a set of orders where each order shares the same start and goal position as the truck drive. Additionally, which we can see then over here, the sequence of truck drives begins with one that aligns with the initial position of the truck. And as the sequence progresses, each subsequent drive starts where the previous one ended. And the objective of our current model is to minimize the normalized average empty space per kilometer across all truck drives, which we can see down here. Having defined the collaborative freighter delivery problem, I am now going to demonstrate that the problem is NP-hard. To establish this, a many-one reduction from the well-known combinatorial problem of bin packing is employed. Note that bin packing is recognized as NP-hard in its optimization version. To clarify, let me briefly revise the bin packing problem. It involves a set of items I, each with a specific volume Vi, and the collection of bins, each with a maximum capacity C. The goal in a bin packing optimization problem is to assign items to bins in such a way that the total volume of items in each bin does not exceed its capacity, while also minimizing the number of bins used. By leveraging this reduction, we show the complexity and computational challenge inherent in solving the collaborative freighter delivery problem. For the proof, let's start with the bin packing problem instance P. We can transform this into a collaborative freighter delivery problem P' into polynomial time by the following steps. The map for P' consists of just 2 points, S and G, connected by a single road. Further, there is exactly one freighter available, and for each bin in the bin packing problem, we introduce a truck in P'. All trucks have the same capacity, which matches the bin capacity denoted by C. Each truck starts at the same initial position S, and additionally, for every item in the bin packing instance, we define a corresponding delivery order in P'. These orders start at S and have a goal at G. Each truck can travel from S to G only once. That means every truck trip directly corresponds to the assignment of one bin. As a result, the minimum number of truck drives in P' will also represent the optimal solution for the original bin packing problem P. In essence, this transformation aligns the two problems and proves the NP hardness of the collaborative freighter delivery problem. Now let me introduce the heuristic algorithm designed to find a near optimal solution. To begin with, it's important to highlight that this algorithm has linear runtime and space complexity, which makes it highly efficient. This efficiency also makes it suitable for implementation in privacy-preserving multi-party computation environments. The procedure optimize repeatedly calls another procedure, solve, for a predefined number of iterations. During this process, it keeps track of the best objective function value and the corresponding solution. The solve procedure builds a solution step by assigning truck drives to transport orders from their start to goal positions. It begins by randomly shuffling the lists of trucks and orders while there are still unprocessed orders. The procedure attempts to create a non-empty truck drive using the function createFillTruckDrive. This procedure works by identifying the first order in the list whose start position matches a truck's current location. If such a match exists, a new drive is created to transport the order from its start to goal position. The truck is then filled up to capacity with additional orders that share the same start and goal positions, and these orders are removed from the list. If no such order truck match is found, an empty truck drive is created using the function createEmptyTruckDrive. This procedure identifies the truck nearest to the start position of the next order and produces a drive without orders, moving the truck to that start position. The resulting drive is appended to the solution and the truck's position and availability are updated accordingly. With the heuristic explained, let us move on to the evaluation, which serves two main purposes. First, to provide an initial proof of concept for the proposed heuristic, and second, to estimate the optimization potential of collaborative freight transport. For this, we use the same map across several problem instances. This map represents a real-world intercity logistics scenario covering 4 Austrian cities, namely Vienna, Graz, Klagenfurt, and Salzburg. The graph shown on the right-hand side over here illustrates this setup. To evaluate the algorithm, we used a publicly available benchmark dataset consisting of 225 problem instances. These instances are defined by the following logistical parameters: the number of freighters ranging from 1 to 5, the number of orders per freighter, which is set to 50, 100, or 500, the number of trucks per freighter ranging from 1 to 5, the volume per order with 3 scenarios where the maximum is 10, 20, or 32, and the minimum is always 1, and a fixed capacity of 32 for each truck. These parameters form a Cartesian product resulting in 225 instances, which we use for evaluation. The dataset is publicly available on GitHub under the link that is shown down here in this slide. Now to the results. The first figure on the left-hand side over here shows box plots summarizing the average objective values for the collaborative and the non-collaborative heuristic variants. The results indicate that the collaborative heuristic consistently outperforms the concurrent one, achieving objective function values approximately 0.15 lower on average, corresponding to a 15% reduction in empty space. Notably, increasing the number of iterations from 1 to 1000 improves results by only about 2%, as the greedy strategy already performs well on the initial iteration. The second figure on the right-hand side over here displays box plots for average objective values across different order sizes. As expected, instances with more orders have greater optimization potential. Conversely, when there are fewer orders, collaboration becomes even more advantageous. This trend is evident from the decreasing difference in objective values as order numbers increase. Finally, let's summarize the key points of this study. In this paper, we introduced the collaborative freighter delivery problem, formally defined it, and analyzed its computational complexity, proving it to be MP hard. We then proposed a greedy heuristic for solving this problem and demonstrated its effectiveness through experimental evaluation. The heuristic's low runtime makes it practical for real-world applications. Notably, its potential for integration with privacy-preserving multi-party computation is crucial for fostering trust among freighter companies and enabling collaborative efforts to reduce empty truck drives. Compared to the non-collaborative baseline, the results highlight significant reductions in empty truck drives, especially in low-order scenarios, demonstrating the clear benefits of collaboration. Last but not least, I want to mention that this work was carried out in the scope of the MooPool project, which was funded by the Austrian Research Promotion Agency. In closing, I would like to thank you for your attention and interest. I appreciate your time and hope you found the presentation informative. I wish you all a good day.